Good morning. So we've been looking at aberrations, and till last week we were looking at the monochromatic aberrations. We ended the week by looking at how we could affect or change the monochromatic aberrations. So for a system with a particular power without changing the focal length of that system, but by changing the shape, we saw we could greatly affect we looked at two particular aberrations, spherical aberration and coma, and you should have plotted that graph in the last lab exercise and seen that for a particular shape you were able to get both minimum coma and spherical aberration. So you see that there is a lot that you can do just by changing the shape. So we are going to extend the idea of how we can control or change aberrations, but before we do that, we'll start by looking at the remainder of the aberrations. And so today's class, we'll look very briefly at also the chromatic aberrations. Chromatic aberration, we discussed earlier, arises because the refractive index and the wavelength are related. So when we've been talking about a lens or a lens with a particular focal length, we never mentioned wavelength, but of course that equation, the focal length equation, has the refractive index in it, and if the refractive index is going to have different values, as it will for different wavelengths, of course the focal length is going to be different for different wavelengths. So what is shown here is the longitudinal chromatic aberration. So by now you know that means we are talking about the aberration or the error along the optical axis. For a positive lens, what you'll find is that the lower wavelengths tend to focus closer to the lens than the longer wavelengths, and that means you have a spread along the optical axis over here. So here you can see it's spread out nicely to demonstrate this. The blue is focused over here, the red is focused over here, and so you have a spread over here, a longitudinal spread of the focus over here. Why does this arise this way? Why is it that the blue rays, the shorter wavelengths, tend to focus closer? It's because most optical materials have N and lambda kind of inversely related, okay. So N is inversely related to lambda for most optical materials. Now, what does this mean when you look at an image which has been taken with a system that has or suffers from longitudinal chromatic aberration? Well, you can imagine if your image plane were as indicated here by this green line, the green light or the middle wavelengths have come to focus here. So you'll have a sharp point which is yellowish greenish, but you'll have this blue red haze around it. Why is there blue red haze? Well, the blue is focused earlier and it has spread at that plane. The red has not yet focused, so it's spread at that plane, right? So you'll have this yellowish greenish focal point and then this bluish reddish haze, and so you often will see images with this kind of purplish tinge, and this is a clear indication of longitudinal chromatic aberration, okay. It's quite common actually to see this. Our mind or our eyes tend to correct for a lot of things, so you don't notice, most of the picture looks well focused, so you might not notice this effect. Now that you're aware of it, I hope that you will notice it more. I don't know if that's a good thing or a bad thing. I made you now aware of how bad pictures are actually. But the point is, you can see that this blue-red haze around the focal point is because of the longitudinal chromatic aberration. This is because the image plane was kept here. I could have kept the image plane at where the blue focus was, right? Then the blur is going to be all the higher wavelengths. I could or push the image plane to where the red focus is, and then the blur is because of all the shorter wavelengths, right? So the overriding color that you see as a blur is going to depend on where you actually put the image plane, okay. But you can see that the circle of least confusion is the central point, and that is typically where people will take their image. Okay. Lateral chromatic aberration, on the other hand, is when you're looking at light coming from an off-axis point, and you can consider it again a variation of magnification, but unlike coma, it's not a variation of magnification with aperture, but it's a variation of magnification with wavelength, right? So different colors are coming to focus on this transverse plane at different points, and so you get a spread in that image plane, and it is really, you're saying the red light has been magnified to this point, the green to this, and the blue to this. So it is a variation of magnification with respect to color. Okay. Again, how will it affect your image? You'll see that, so the upper image here has been taken with the system where there is minimum or no chromatic aberration, and the lower picture shows the chromatic aberration, and you can clearly see this kind of rainbow effect because each color is coming to focus at a slightly different location, and is very, very clear. The aberration is very clear. You can see how it overall gives the image a very blurred effect, right? So you really, it's not that you have nice clear images, you have this very blurred effect caused by different wavelengths coming to focus at different locations. Okay. I don't want to go into much detail of the chromatic aberrations, but what I want to now do is spend some time on how would we correct these as well as other aberrations. Okay. So let's go back to the example we were looking at in the last class. In the last class, we said, let's take a particular lens, a single lens, and these were the same conditions for that lens. It was focal length 100 millimeters. We are assuming the object is at infinity, but you have a field of view of plus minus 17 degrees. Okay, so that's the system that you're studying. This was the system you looked at, and then you changed the radii of curvature such that the focal length stayed at 100 millimeters, but you had different shapes, and then you could observe the different aberrations for those different shapes, okay, or rather how they varied with respect to the shape. Okay. So we are taking the same system. Now this was the graph that you should have plotted, or something similar to this. We only looked at coma and spherical aberration. Did any of you look at any other aberrations? The reason that I asked you to plot only coma and spherical aberration is because shape does not affect other aberrations. Right? So if I were to plot what are the other aberrations we could have looked at, we have astigmatism, we have distortion, we have field curvature, we have the the chromatic aberrations, right? So it turns out that if I look at the axial chromatic aberration, the shape is not affected, the aberrations are not affected by the shape of the lens. So I didn't ask you to plot that, although now you could go back and look at that and convince yourself that changing shape does not change the chromatic aberration. So there was no purpose in plotting it here except perhaps to see that it is unaffected by the shape. We are not saying that chromatic aberration does not exist. For a particular optical system, and this is what I mean by optical system. What is its speed, what is its focal length, what is its field of view? For a particular optical system, there will be some axial chromatic aberration, there will be some astigmatism, there will be field curvature. But if you were to change the shape of the system, of the lens, these aberrations would remain constant. They were not going to increase or decrease. So there was no purpose in plotting it here. So this graph, and I want you to go and try it out. take any one of these aberrations and just add that data along to what you have plotted earlier. Convince yourself that yes, shape is not affecting these aberrations. On the other hand, I want to do something to affect these aberrations. So I have looked at shape, but we had listed out a whole range of different parameters that we could play around with to affect the aberration. Shape was just one of them. The other one, very important tool, is the stop itself. Now, in this example, of course, there is a stop in this example. If you don't say anything, if you don't add anything extra, the lens mount or the lens diameter itself acts as the stop of the system. So, though we haven't explicitly said anything, the other point I should add is that in this optical system, the aperture stop is at the lens itself. So now if I want to play around with the aperture stop and find out its effect on aberrations, or if it has an effect on aberrations, what I'll do is now separate the aperture stop from the lens. So I will add an aperture stop to the lens and will vary one parameter of the aperture stop. So I'm not going to vary size of the aperture stop. I'll say I have an aperture stop of a certain size and now I vary its position with respect to the optical axis. Okay, so you understand what we're setting up. We are now saying our system is not just an optical axis with a lens, but it's an optical axis with an aperture, and a variable now for us is d. D becomes a variable. I've drawn it here with the aperture before the lens. But of course, the aperture could even be after the lens. So the aperture can be anywhere along this optical axis. Okay. Now, how does this affect the aberrations and which aberrations does it affect? We saw shape didn't affect a bunch of aberrations, right? Okay. So, if you now vary the stop, now this is a graph plotted by varying the stop. What does it mean? Only two aberrations are plotted here again. So this shows you the coma, this shows you the tangential field curvature. So blue is tangential field curvature, this is coma. What are the different points plotted for? So this is the position where the stop is at the lens itself. So this axis here indicates the distance of the lens from the stop. Okay. If I have the stop in front of the lens, so in this case, this is the lens and the stop is here itself. Minus 10 means the stop was moved to this position. Minus 20 means the stop was moved to this position, and so on. Plus 10 means the stop was moved to after the lens. Okay. So in every case, we are taking the same optical system, but I have to choose. We had a range of shapes here. So the graph that I am showing you now was taken for this particular case. Okay. We have picked the case where the coma is not 0. We have not picked that case because we want to start out with some value of coma to see how it gets affected by moving the stop around. So we are taking this case. All the other parameters of the system are the same: focal length, speed, field of view. But you have taken this shape and we are moving the stop before the lens, at the lens, after the lens, and for every case plotting the aberrations. Again, I've picked some aberrations. Now, it would normally, when we want to compare graphs, we take the same parameters. So I studied spherical aberration and coma before this exercise. Logically, I should study spherical aberration and coma after this exercise. Why have I not done that? The spherical aberration is a on-axis aberration. I can put the stop wherever I want. It isn't going to affect the spherical aberration. So I could plot it, but I won't get any information from plotting it. It is unaffected by the stop position, right? So spherical aberration, axial chromatic aberration, they are unaffected by the stop position. Axial chromatic aberration is affected by the size of the stop, right? If I were to change the size of the stop, I would affect the axial chromatic aberration. So, stopping down a system is one way of reducing the axial chromatic aberration. But here, we are now, each time in these graphs, we are varying one parameter and one parameter only. In the previous graph, we varied the shape. Here, we've picked a particular shape and we are varying only the location of the stop, not even its size. So, axial chromatic aberration is not affected. Spherical aberration is not affected. Only parameters that are greatly affected are coma and the tangential aberration. So, astigmatism. Astigmatism and coma are affected, and you can see they are affected a lot by the location of the stop, and it should not be surprising to you, because if I look, say this is my optical axis, this is my lens, and I have rays coming in from an off-axis point. I think I drew something like this in the last class as well. Which set of rays reach this point depends on where the stop is. If I put a stop here, I am cutting off these rays. If I put a stop here, I am cutting off a different set of rays. So, the stop location greatly controls the path of rays through the lens, which rays actually make it through the lens to the image. And this is true because it's coming from an off-axis point. So, coma and tangential aberrations, astigmatism, are greatly affected. And the moment I say greatly affected by, it also means this becomes the tool or one of the tools by which to control or minimize these particular aberrations. I won't use stop position as a means of controlling spherical aberration. If you went to Oslo, set up a system and made your variable thickness where it was setting the distance or the location of the stop, and you said the operand I'm optimizing for spherical aberration, you can optimize all you want. The spherical aberration is not going to be minimized, because that's not the right variable to choose to minimize spherical aberration. Okay, but coma and astigmatism will be greatly affected. Okay, it turns out lateral color is going to look something like this. I not get the graph right, but something like this. So, I have a linear variation. Distortion is something like this. Okay, actually this 0 matches with this 0. Distortion goes to 0. This should be at this point. Sorry. Right. So, this is the point where the stop is at the lens itself, or you could think that the mount or the rim of the lens acts as the stop. And then you've put the stop either before the lens or the stop is after the lens. Okay. Now, you see in this case, all that you did was move the stop and then measure the aberrations in each case, and you've plotted here the two aberrations that vary greatly depending on the stop position. And they are both off-axis aberrations, coma and astigmatism. Okay, I'm saying astigmatism is off-axis, assuming you have a circularly symmetric lens. So, the asymmetry is coming because the point is an off-axis point. Okay, you can see that just by moving the stop, you have found a place indicated by this arrow where coma goes to 0. So, for a given optical system, there is a natural position where coma goes to 0. At that same position, you find that the tangential field aberration is at its minimum value. It's not 0, but it's at its minimum value. Remember, what was tangential field astigmatism? This is my planar paraxial plane, but this is my actual paraxial image. It's on a curved surface, not a flat surface. And we said the sagittal will be like this and the tangential would be like this. So at this distance, I'm measuring what is the error of the tangent, right? But if I put the stop at a certain location, basically I'm cutting off these rays. So you can see that I'm reducing this error, right? So at this particular distance from the lens, in front of the lens, when the stop is this distance in front of the lens, you have the minimum tangential error. And it's also where coma goes to 0, okay? Because you have this position where coma goes to 0, and you could take any, this was plotted for the case where we took a particular shape. You could take any of those shapes, right? I pulled out one particular shape, but you could take any of those shapes, keep all the remaining parameters constant and plot this graph. The curves would look slightly different, but you would have in each one of those curves a location where coma went to 0. Okay, so it won't necessarily be at the same distance in front of the lens. Depending on the shape, the location of the stop where coma goes to 0 will have a different value, but there will be a place where coma goes to 0. Okay, therefore this is called the natural stop position. So what I will ask you to do in tomorrow's lab class is to go back and replot. That exercise in tomorrow's class is to go back and replot the aberration curve. But last time all you did was vary shape and then plot the aberrations. Now I'm going to ask you to vary the shape, move the aperture stop to the position where coma is 0. In other words, move the aperture stop to the natural stop position for that shape and then plot the aberrations. Which aberration will you not plot in the exercise? You will not plot coma because coma is 0, right? So in the last class you definitely plotted coma, but now we are saying each time move the stop to the natural stop position. You are going to have an operand saying select coma and make coma 0, and your variable for that will be stop position. Okay, so if you do that, this is a kind of graph you'll get. Now we are looking at all the aberrations. In the previous exercise we looked at only spherical aberration and coma because the others stayed constant with respect to lens shape. So there was no purpose in varying or plotting them. They all had some value, but that value stayed constant. So you didn't plot them. But now you are doing several things. You're going to change the shape, and for a particular shape you're going to find the natural stop position, and then you're going to look at all the aberrations. So of course they do vary, and you can see that there's a lot of variation. There's a lot of information in this graph. Okay, so let's try to look at what all these lines mean. First point to note is we haven't plotted coma here because we are looking at the case when the aperture stop is in the natural stop position. In other words, we are saying coma has been minimized. So there's no need to plot it. But every other aberration is plotted here. In addition, you have a curve, this blue curve, which tells you where is the stop in each case. And you can see for this lens, this is the stop is at the lens, and that means for all these shapes the stop is in front of the lens, and for all the subsequent shapes the stop is after the lens. Okay. Now let's look at, we are plotting spherical aberration here, okay, because we are taking shape as well into account, right. So you can see that the spherical aberration, it doesn't look very different from its previous graph. It shouldn't, because basically what has changed spherical aberration here is only the shape, not the stop position. So it is the same as the previous graph. However, the other coma is not plotted, and we have introduced all the other aberrations as they are affected by the stop location. So let's take spherical aberration and this tangential astigmatism. Okay. Now you can see where the spherical aberration is minimum. Now, I say minimum, but if you look at the value, this is the least negative value. So value wise it's maximum, but it has the minimum, its absolute value is what is important in terms of how badly does it affect the image. So here's where I have the minimum aberration, where I see the minimal effect of spherical aberration is at this point here. You might think, well, that's a good place to choose a lens. That's a good, when I say good place, what does it mean? I'm saying let's choose this shape. Many aberrations are 0 at that point. Spherical aberration is minimum at that point. But astigmatism is not minimum at that point. In fact, astigmatism is maximum at that point, right? So if I was designing a system which was meant for on-axis imaging, I would happily choose this shape. What shape is it? It's almost plano-convex. Right? I would choose this shape because I've minimized lateral color, I've minimized distortion, I've minimized spherical. In fact, distortion, lateral color are 0. And the natural stop is at the lens itself. Spherical aberration is minimum. So this is a good system to pick if you are trying to do on-axis imaging. But astigmatism comes from off-axis points. So if you were trying to do off-axis imaging, if you knew your system had a wide field of view and you're going to have astigmatism in your system, the fact that the value is over here means that this is not a good shape. So a better shape is when this curve, where this curve reduces. Now where does it reduce? It reduces for the meniscus lenses. So if I was going to do imaging in a system where I know off-axis rays are going to come in, where I expect to see astigmatism, I would rather pick a meniscus lens than a plano-convex lens, knowing that the spherical aberration is not 0 there. So I might not pick this place because I have a large amount of spherical aberration. Maybe I'll pick something here and I compromise between the astigmatism and the spherical aberration. Okay. So this in fact is the shape that is used in these very inexpensive cameras, right, where you have one lens, and that lens typically will be a meniscus shaped lens. So you are compromising between the spherical aberration and the astigmatism because those lenses expect a slightly wider field of view. They're not only going to be used for on-axis purposes, you expect a slightly wider field of view. So plotting graphs like this help you to decide depending on your imaging system. Right? You look at this and you decide what is important, or based on the kind of imaging I'm going to do, how I expect the light to be entering my system, what is the required field of view. I would go and say which are the aberrations that will not be affected or are affected less, or where are they minimum. Let me pick that shape. And in this case, we are not asking where shall we put the stop. We are saying the stop will always be put at the natural stop position. So you've got rid of coma, and remember we saw how bad an aberration coma was. So it's really good to know that there is some justice in this world. We are given a bad aberration, but we are also given a way to fix that bad aberration. Okay. So let's say you were given system and you have looked at or calculated all the aberrations of that system, okay? And now you make some slight change in the system, okay? So what do I mean by slight change in the system? You don't change the focal length of the system, but let's say you change the aperture. So the aperture you started with, you've calculated aberrations for a system with a certain aperture, a certain field size, and a certain focal length. And you have now got the values for all these various aberrations for a particular optical system. Now you go into that system and you change Y and you change H. It turns out you don't have to recalculate everything, because the way the aberration is dependent on aperture and field size. If you have already calculated those values, you can just use the relationship between the aberration and that particular parameter to recalculate. So let's take, for example, a case where you had a certain aperture, and let's say, so in this example, let's say you increase the aperture, okay, so that it is 1.5 times larger than what it was originally, right? How does its longitudinal spherical aberration vary? So this is, let's say, longitudinal spherical aberration. If earlier the longitudinal spherical aberration was some, let's say, L1 units of length, then the new LSA will be 1.5 times L1. Okay, so you don't have to go back and redo that calculation. Or on the other hand, let's say the coma, you have increased the aperture by this much. Let's say you also decrease H to 0.5 its original value. So what is the new coma then? If the original coma was C1, then the new coma, it's y squared, so it will be 1.5 squared, because it's, and it will be 0.5 comma, it's only that, into C1, okay? So I just wanted to, don't bother too much about this table, but I wanted you to always keep in mind that these things are not unrelated. You are arriving at the aberrations for a system given that you have a certain aperture, you have a certain field size, you have a certain focal length. You can also find out versus focal length and so on. If you change one parameter slightly, the aberrations are going to change in a very specific way because they are related to those parameters of the system. Okay, so that's the main point to take away from this table. Okay, you don't have to recalculate and redo everything. You're not changing the system completely, but you are affecting the aberrations. Okay. Okay. So let's look at one correction in some detail. So axial chromatic aberration, we saw that for a positive lens, the blue wavelengths come to focus closer than the red wavelengths, and that is because typically n and lambda are inversely related for optical materials, which means that the angle of deviation is going to also increase for as the refractive index increases. Okay. Now, how do I do a correction? Clearly, to do a correction, I need to add something to my system. So we are going to make the assumption or say, let's see if we can do the correction with two lenses. I keep in mind that this combination must preserve the focal length. So I have a system and I want to have a desired focal length, but I want to minimize axial chromatic aberration. So I want to now say I'm going to add another lens and adjust the individual focal lengths or maybe the distance between them such that the overall focal length of this system stays as my requirement, but I have reduced an aberration. And in this case, the aberration we're looking to reduce is chromatic aberration, okay, axial chromatic aberration. Now, you can work it out, the focal length for a system of with two lenses and a distance d apart. So, imagine you have two thin lenses with a distance d apart, is going to be this equation. I can write this in terms of the individual focal lengths, and this rho 1 is nothing but the shape factor. Okay, so it would be 1 by R1 1 minus 1 by R2. Okay, so this is nothing but F1, this is nothing but F2, and I've basically rewritten this equation, expanding it in terms of the refractive indices and the shape of those individual lenses. Our goal here is that blue light and red light should focus at the same point. I want this combination to give me the same focal length for two different colors, and that's the condition I'm setting over here. So, I will now write this equation. So, 1 in terms of refractive index for blue and red light. So, that's all that equation 2 is. I've written equation 1 for red light. That means I've taken the refractive index N1 as N for red light, and then the right hand side of the equation is the same equation 1, but now it's written in terms of the refractive index for blue light. To make it simple at the moment, to get the idea across, let's take the case where D is equal to 0. Okay, and if I do that, I can reduce this equation to this. So, we are saying, or what is this equation saying? If I take the ratio of the shape of the two lenses that I am using, in order for them to, this combination to have the same focal lengths for blue and red light, the refractive indices must have this particular relationship, N2B minus N2R divided by N1B minus N1R. Okay. Now, I have chosen one lens. This is lens F1. It has a certain refractive index for red light. It has a certain refractive index for blue light. I have another lens. I'm just drawing it as a convex lens. I don't know. Please don't think it's a convex lens. We don't know anything about whether F1 is positive or negative. We are just taking a lens with a certain focal length. This has another, so this has one glass. It's made of one material. Each of these is made of one material. The material of the first lens has N1R for red light, N1B for blue light, and the material of the second lens has N2R for red light and N2B for blue light. And if the values of these refractive indices are such that they satisfy this equation, then in principle I should be able to get, okay. But it's not that simple to just get two materials like this. So, what else can I do? So, let's go back and say, let me just take these two lenses and send some wavelength through them. Okay. So, here I have looked at if there was red light going through, there's red and blue light going through. Here, if there's red and blue light going through the second lens. Now, I say through each of these lenses, I'm going to send a third wavelength, yellow, and I take the ratio, right, of, so this is nothing but the ratio of the focal lengths for a third wavelength, and that wavelength is yellow. So, now I am saying the refractive index of the first light when yellow light goes through is N1Y, refractive index of the second lens when yellow light goes through is N2Y. So, now I have an equation here which is a ratio of the shapes of these two lenses in terms of refractive indexes of red and blue light. Here I have a relationship for the same ratio, but now in terms of the refractive indices of the yellow light going through these two different lenses. So I can equate equations 3 and 4 and end up with this relationship. And doing so gives us an insight into one of the parameters used to classify glass materials or optical materials. If you take this divided by this, why am I picking those terms? Because those are all the refractive index terms for the glass N2. What is the second lens? What is its refractive index for blue light? What is its refractive index for red light? What is its refractive index for yellow light? So that is this relationship. Similarly, I could take this and this, and that is this relationship. So I have the first glass F1, and of course it will have 3 different refractive indices for each of these wavelengths, and I have the second lens F2, and it has 3 different refractive indices for the same 3 wavelengths. This ratio, when we invert it, is called the V number or the Abbe number of the material. Now look at this ratio. What is it telling us? It has, if I look at the spread of wavelengths, I have blue, I have yellow, and I have red, right? That's how the wavelengths are spread out. And this relationship is giving us the difference between the yellow or the middle refractive index and 1 divided by the difference between these two refractive indices. Now, if I wanted a material with less dispersion, right? What is dispersion? What is dispersion? So it's the spread of different wavelengths. Right? When will I have less chromatic aberration? I'm going to have less chromatic aberration if the wavelengths don't spread out. The less those wavelengths spread out, the better for me. So I want a material with less dispersion. What kind of V number should I have? A large V number or a small V number? Look at the relationship. Exactly. So you want to have a large V number, right? So large V number means less dispersion. Why? Because when do I get a large V number? When this, that is N2B minus N2R, is small. Ideally, it should be 0. If it's 0, it means the refractive index for red light and blue light are the same. So whether blue light or red light goes through a lens, it will see the same refractive index, therefore it will have identical focal length. So ideally, N2B minus N2R or N1B minus N1R should be 0. Now, if it was 0, your V number would be infinite. For naturally occurring optical materials, N2B or the refractive index for blue light and the refractive index for red light, this is like one of those twister things, she shells, seashells. I'm getting my R's and L's all mixed up. These two refractive indices have to be as close to each other as possible. For optical materials, you'll never have a case where they are equal. But you do have some glasses where the values will be closer than for other materials, right? And we've just been going into Oslo and saying, picking a glass type DK7. Now what you will find is you need to be able to play around with the glass types. We said 2 lenses. So I want to pick these 2 lenses such that the combination gives me less dispersion. Okay, so we are getting towards how we can do that. So remember this equation, right? I can rewrite this in terms now of the V numbers. So if I'm able to arrive at this somehow in my optical system, then I know that I can get a system where blue light and red light come to focus at the same point. Now, either I could do this by saying I should have materials where the dispersion is opposite. One has positive dispersion, one has negative dispersion. Or I will choose, and what does that mean? That means in some case, ND is never going to be less than 1. Refractive index is never going to be less than 1. So the numerator is always positive. I can never make this numerator negative. You might think somehow I need to get this to be negative. But again, that is not natural for our optical materials. It is going to be positive as well. So how do I get negative dispersion? I don't get it from the V number then. I will get it from using two different focal lengths, a positive focal length and a negative focal length. So my combination then is going to be a convex lens and a concave lens. One point to note is that the V number is a number that's assigned as a standard number to any glass type. So if you now go and look at Oslo, open up an optical catalog, you can go look at the parameters of the glasses. And one of the parameters they'll give you is the V number. So the V number you can see is written in terms of 3 refractive indices, yellow, blue and red light. So they use standard sources, and at those specific wavelengths is where they find the V number of a particular glass type. Okay, so these are the sources. So it's the helium D line is 587 nanometers, hydrogen F line, hydrogen C line. These are the 3 wavelengths. These are the standard sources that are used to calculate the V number of any optical material. Okay. Typical V numbers for glass types are optical materials. The dense flint, light crown, fluorite crown, these are all glasses. This polycarbonate plastic is a plastic, but these are the V numbers, and you can see they range from 20 to 85. And the BK7 glass that we keep using, these are the refractive indices at these 3 sources, and it has a slightly higher end V number of 64. Okay. So we'll continue with this tomorrow. What have we done in today's class? We moved from looking at monochromatic aberrations to chromatic aberrations. Right? We did that very briefly, but then we went back to those aberration curves and looked at how does aperture position and how does shape, how do they affect the aberrations, which aberrations they affect. And this is part of the exercise you'll do in tomorrow's lab, is to plot and show which are the aberrations that get affected by these parameters and how much they get affected by these parameters. Okay. We then, in the latter part of the class, took one of the aberrations. We took the aberration of axial chromatic, and we said, how do we correct it? So we are looking now at how do we correct it, and that is what we will continue in tomorrow's class.